All right, it's time for us to get started. This is our last day before the exam, so if anyone has any questions related to the study guide, the exam, now that it's written, the exam format, anything else along those lines?
The whole thing could be about testing.
Yeah, but anything on the study guide, so we haven't really done anything, I don't wanna test anything from the review section since technically that was tested in a prior class or could have been tested in a prior class. And I don't know where you all are coming from, so I don't wanna create any kind of uneven balance from the quality of those instructors or anything that you retained or was presented differently amongst different people. So we're only gonna test the stuff that's precisely covered in this class in a full enough detail that I would expect that you walk away with some understanding. So that's only been testing.
Is it all short answer?
There are a lot of it is short answer. There is some application as well.
Multiple choice.
There is one multi-select, but for.
Let's go 20% chance.
I think the student.
It's not a multiple choice, it is a multi-select, so it's something like you have lots of options, pick some of them. I don't really like just the straight multiple choice. Because then it's either full credit or no credit, because you have no chance to explain your answer or show your thought process. I'm the kind of person who always wants to see and hear your thought process, so that if you have partial understanding, you get partial credit. So there is partial credit on every problem on the exam, including the multi-select.
Some of these are like be able to write a test suite. Are we going to be like handwriting a bunch of code, or is it more like pseudocode?
There, you may need to be able to write specific tests, but as I promised on the exam is the list of the assertions. So you do not need to put those on your note card or memorize them in any capacity. You will have that slide that has all of the assertion methods, the order of their parameters, where a message goes in that if you're going to include a message with your assertion, all of that is on the exam.
You said there's gonna be extra credit.
There are 104 possible points on the exam and I will grade it out of 100. There's no extra credit question, the 4 points are just kind of baked into the exam. When I finished applying points, it just turned out that there were 104 points on the exam, rather than trying to finagle, where can I remove points from the exam? It's like, all right, I'll grade this out of 100. There are only 3 problems, but the problems have up to 6 subsections, and some of those subsections may require a multi-part answer. So something like describe 3 somethings is one of 6 parts of one of the 3 questions. So there is one application question of those 3, and the others are all kind of the short answer. Show me the intuition or the logic behind why we do what we do. Because we haven't done a ton of application in here, the application is very, very limited. I don't expect you to be able to apply unit tests to production level code. It's going to be very simple, very easy to understand code, and the test that you write for it should be fairly obvious what you need to do. So there's nothing like you need to go look at external resources to be able to be successful on the exam. Everything that you need should be there in basic Java construction, and knowing what a unit test is and being able to read simple Java code.
So nothing like here's an entire 2 classes, now write that's all, right?
No.
Oh, that's
Any other questions about exam stuff? All right, I'm gonna try to knock out 2 Project Euler questions today because one of them is actually very interesting in the application of it. So let's start. We're gonna do 4 and 5 today. So let's start with number 5, because I think this one's actually going to be easier than 4 for us, if we think about the problem in a certain way. So the problem reads, as usual, it gives you an example before it gives you the question. The example is 2,520 is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. What is the smallest positive number that is evenly divisible by all of the numbers from 1 to 20? And I will argue that we do not even need to write a program for this. And in fact, it uses some of the procedures that we have written for previous problems that we have already solved. So this is a very interesting application where you can shortcut brute forcing this by just understanding how a number is composed and also by understanding the fundamental theorem of arithmetic that we talked about last week. So I have no idea what people's math background is, but in order to be evenly divisible by all the numbers from 1 to 20, what are your initial thoughts? What's your initial thought about how you might want to tackle this?
We can cut down the list of numbers we actually have to check for, such as, 5 already goes to 10, so we don't need to check for 5, we just need to check for 10. But that also means you don't have to check for 2. And if we go to 20, then we also don't have to check for 10 because 10 is a multiple of 20, which
Sure.
then cuts down what numbers we have to look for.
So where should we, if we were gonna do this iteratively, where should we start? What's the first number we should check? Is 7 possibly gonna be divisible by 20? Is the number that we produce for this has to be divisible by everything from 1 to 20. So a very basic way of starting this process would say, well, if it needs to be evenly divisible by 20, then we should check multiples of 20, right? We can start checking 20, 40, 60, 80, 100. And there's no reason to check things like 21, 22, 23, because it's just not going to be divisible by 20. And there are fewer multiples of 20 between 20 and whatever this number happens to be than there will be multiples of 19, or multiples of 18, or multiples of 17. So a brute force, the true brute force way would be check 1, check 2, check 3, check 4. We can shorthand that a bit by saying, let's check 20, 40, 60, 80. But I'll argue that there's an intuitive, even shorter way that'll get us right to the answer. So you're saying check 20 factorial?
20 to 11.
So if we check 20 factorial, that will certainly be a number that is evenly divisible by all of those numbers. But is it the smallest possible number? So then how do we start being able to factor out, and is 20 factorial representable? Like how big is 20 factorial?
Pretty big number.
Do we want to see if the calculator app can actually calculate that? We can't do, oh, it does allow factorial. 20 factorial.
Is your answer?
2 quintillion, 432 quadrillion, 902 trillion, 8 billion, 176 million, 640,000.
Give me a second while I check that.
It's not the right answer. It is an answer, but it is not the smallest positive number that is evenly divisible by all of those numbers.
Divide that one by 20. And we're just gonna keep going until we get it.
Well, eventually the number would not be divisible by 20. Thankfully, it's only 1 to 20 and not like 1 to 100. But I would argue that the process that I'm going to introduce here would work without being able to represent something like 100 factorial, which as soon as we get a much bigger than 20 factorial, this is going to be crazy. So how many of you are in or have taken data structures? Just about everybody. For those of you, have you gotten to computational complexity? Do we know what I mean by computational complexity? So it's basically the mathematical formula for how a program grows from input to output if the input grows. So as the input gets bigger and bigger or longer and longer, what is the mathematical function that maps to how long it takes to produce an answer? So one of those functions would be factorial. In fact, factorial is the worst possible reasonable solution to a problem. So you can imagine an example of a factorial is, all right, we have an array. We want to sort this array. Think about the stupidest way you could think of to sort an array of a particular size. What is the dumbest method that will eventually terminate?
Yes, randomly.
Generate a random number, or generate these completely randomize the order, check if they're in order. Completely randomize the order, check if they're in order. Completely randomize the order, check if they're in order. Does it seem intelligent? But we can analyze this mathematically to say, how many times do we need to do that to, on average, get this first position right? Let's say this array is of length 6. How many random permutations do we need of this to get this right once on average? 6 times. Who knows about the rest of this array, but we need to do it 6 times to on average get this position right. Given that we got this position right, how many times do we need to get this position right to on average get this position right? 5 times. So here's an example of a really lousy algorithm that will eventually terminate, but has a growth factor of the factorial of the size of the input. So that's just an example of computational complexity. You can analyze any algorithm and figure out what is the mathematical function that maps how it grows as the input grows. As this array grew to size 7, that would be 7 factorial, 10, 10 factorial, 20, 20 factorial. And we already see how fast 20 factorial grows. This would take over 2 quintillion attempts at randomizing to just get, on average, to be able to sort an array of size 20. Can anyone visualize how big 2 quintillion is? That's really difficult. That's more than 1,000, 1,000, 1,000, 1,000, 1,000, 1,000.
That's space big.
Yes, that is too big. Anyway, that's kind of an aside, but the idea is factorial is really, really bad and grows inappropriately for being able to solve the problem. So yes, this is only asking us about 20, but if it asked us about something that was significantly larger than 20, then starting with the factorial wouldn't really work. So let's try to come up with something more intelligent. How could we use this concept of the fundamental theorem of arithmetic? We know this number is divisible by 2 and 3 and 4 and 5 and 6 and 7 and 8. If we list all of the primes between 1 and 20, how does this help us solve the problem? So we know 2, 3, 5, 7, 11, 13, 17, and 19 are all of the primes between 2 and 20.
Let's get all the numbers that are just factors, prime, smaller numbers or bigger.
Kind of, yes. So if we multiplied all of these together, we would get something that was divisible by all of the primes, but what about the multiples of the primes? Like 4, we need it to be divisible by 4. Nothing in here accounts for that. But what if we square this too? That allows us to account for 4. So we could start thinking about, okay, this allows us to account for 2, 3, 4, 5. 2 times 3 is 6, 7. Can we handle 8? 2 cubed, so we should change this to be 2 cubed. 9. 3 squared. 10, 5 times 2. 11. 12, where's 12 in this?
It's a mix of 2 2s and 1 3.
Yeah, 2, 2, and 3 gets us 12. 13, how do we generate 14?
2 and 7.
2 and 7? How about 15? 3 and 5? 16?
That's two.
Yeah, we need to change this exponent to 4 to be able to represent 16. 17 is there. Where's 18? Three squared times 2? 3 times 3 is 9, times 2 is 18. 19, and then where's 20? Yeah, 5 times 2 times 2. So now we've generated all of the prime numbers that allow us to represent whatever this number happens to be. And note that this 2 to the 4th accounts for, even though this represents 16, it really shows us how many times we can divide out this number if we were to take the factorial and start to be able to divide this out. So we would have 16 and 8 and 4 and 2 in this. And we're saying that we don't need to do that, we only need 16. So if you multiply all of these numbers together, 2 to the 4th times 3 squared times 5 times 7 times 11 times 13 times 17 times 19, that's your answer. It's less than the factorial, and you don't need to be able to represent the factorial to be able to get there. You've factored out from the factorial everything that matters, and you've also represented it in a form that is significantly easier to represent than a really large number. If you care about what this value is, you can multiply it together, but here you have an expression that's going to give you the right answer. You can find every number from 2 to 20 out of some combination of these primes. So you use the concept of the fundamental theorem of arithmetic to be able to answer this question.
Would we be able to do the same thing for like finding the lowest common denominator of all, of like 0 or 1 through 30 in a similar way, just finding the numbers that would?
Yeah.
Okay.
Absolutely. You generate all the primes up to 30, and then you would figure out what combination of primes do I need to be able to come up with every combination between 1 and 30. And then multiplying that together would give you the answer. So it is a general solution, not just for 20, but it will work. You just generate primes up to, if we call this 20n, we generate primes up to n. And then we make sure that we can come up with every number in between by coming up with their breakdown of the associated primes that make up those numbers and account for them. So there's a mathematical hack to this. So rather than even writing a program, if you know enough about numbers and math, you don't even have to write a program. You can just think about how are these numbers related, shortcut the entire process of writing a program, and just come up with the expression yourself. So this is an example of a problem that does not need a program. So we are not going to consider it anymore because we already generated the solution. Just for fun, I verified it, it's right. And it's also smaller than 2 quintillion. It's only, I think, 250 something million. So something that's digestible. If really large, it's still digestibly large, rather than 2 quintillion, which is kind of undigestibly large. All right, the real question we're going to tackle today that will need a program is problem 4, the largest palindrome product. So we know what a palindrome is, right? A number or a string that reads the same forwards and backwards. Largest palindrome made from the product of two two-digit numbers is 9009, which is the product 91 times 99. How are we going to find the largest palindrome made from a product of 2 three-digit numbers? So let's think about that for a while. I'm at least not aware of an easy mathematical hack for this. So this is something that we're going to need to use some iteration for, or some recursion for. So start talking to your neighbors and see if you can come up with a reasonable approach to this. What do we think the answer to this is? There are a million possible combinations here. How long will that take a computer to brute force check?
Wouldn't it be less than a million, because you don't have to check 0 to 99? Because those aren't 3-digit numbers in this case,
That is true.
so.
This kind of gives you a ballpark worst case. It is less than this, so you could really say it's less than a million. 900 times 900. So it's smaller than this, but not significantly smaller than this. 810,000, I think is 900 times 900. Well, we'll have a quick discussion about whether or not that's feasible. What's a computer capable of? So yeah, when we have a CPU, and this is going to be passing all of these through the CPU. When you have a CPU, what is its speed measured in?
Hertz.
Yeah, it's measured in usually billions of hertz. If you have something that says gigahertz, that stands for billions of hertz, which stands for the number of clock cycles that you get per second. So it's actually capable of, not every one of these is going to take one clock cycle, but close enough because it's multiplication. If all you're doing is a multiplication in your loop, it's going to take a single clock cycle. So a 3 gigahertz processor with a single core is capable of 3 billion calculations per second. So whenever you have a problem that says something like there are a million things to check, it's actually possible to check this brute force. It seems like a large number to us as humans, but to a computer, this is nothing. And the time it takes for you to mentally answer the question, are you hungry right now? I'm sorry if you weren't hungry and now you are hungry because I mentioned food. And the time it took you to process that, this computer would have finished this problem on a single core. Which is really interesting to think about, the power of a computer. That's really cool. So there's nothing wrong with solving this problem brute force. Now, if we ask the question for 4-digit numbers or 5-digit numbers or 6-digit numbers, we would be having a different discussion. So maybe it's worth thinking about what is the easiest way to solve this problem in case this ended up scaling past 3-digit numbers. So you can come up with a solution, but once you come up with a solution, think if there's any way you could improve your process. All right, back to it. I see a lot of people working individually, which can be great if that is your preferred method of working, but I also would love to see some collaboration in here as well. So if you have any inkling of talking to your neighbor and discussing this with them, feel free to reintroduce yourself and work together.
And we'll go back. So. Oh,
Let's start thinking in terms of efficiency. What is the largest possible number that we can produce with a product of 2 3-digit numbers? What are the two numbers? Not the product, but the two numbers. 999 and 999. I'm gonna turn this into two columns, and we're gonna start to see how this evolves. What is the next largest number? Well, I guess first I should ask the question, is it gonna be possible to write this as a list that just keeps getting smaller and keeps getting smaller and keeps getting smaller? The answer is yes, we can. We have to think a little bit critically about the shape of multiplication. Remember that I talked about multiplication just being kind of like rectangles, where the most area you can get per perimeter is with a square, and the least you can get is with one really, really short side and one really, really long side. So what is the next largest combination?
999 times 998.
I'm actually gonna write them in exactly the opposite order, but yes, I'm gonna do 998 and 999. What comes next? Which one is larger? 997 times 999 or 998 times 998?
998 times 999.
Yes, this one is larger. Why? How do we know that? These sum to the same value, which means they have the same perimeter. And this is closer to a square than this. That's the only two pieces of information that you need to know. These two numbers are closer to each other and they add. If you add number 1 to number 2, they add to the same value. So the next number we want to consider is 998 times 998. What would come next? Is there anything left that we want to test with the first number being 998? Assuming that the left number is always going to be equal to or smaller than the right number. I'll put that constraint on there because it will make this problem easier.
I mean, we should check 997 before we keep going down, just in case. Right?
If we do that, the first number could be 997. If we're making the constraint that this number is smaller than this number or the same as this number, then we'll hit 997 times 998 when we consider 997 on the left side. Yeah, so we're done now with 998. We want to start considering 997. If the first number is constrained to be 997, what is the largest possible number we could produce? 999. And we already said that this number is smaller than that number. So far, every number is smaller than the last one. What's the next number we should check?
997, 998.
997, 998? What's the next number we should check? Are we done with 997? Should we move to 996 yet?
We have 997 squared.
Yeah, for the same reason that we wanted to consider 998 and 998 before 997, 999, because they sum to the same value, and this is closer to a square. We want to consider the square of 997 before we move on to anything with 996. Uh-oh. Which one of these is larger? They no longer add to the same thing, so we can't be sure anymore. But this will, at least algorithmically, be a reasonable start. It would be nice if once we revealed a number where the product was a palindrome, we could stop. But I would argue that if we're considering everything here that is 99, we just have to make sure that we iterate through, once we find a single palindrome, we just need to go down and consider some numbers that are larger than this until we find some termination point where we guarantee that every other number that we haven't seen so far is a smaller product. And that will allow us to look at fewer pairs of numbers than we would if we started by counting up, or by doing 999 times 998, 7, 6, 5, 4, 3, 2, counting all the way down. There's a slightly more intelligent process that allows us to kind of weave our way through this rather than check some numbers that are going to be suboptimal. So that's kind of a thought process about the order in which numbers should be considered. The other part of this is being able to identify palindromes. There's an easy way and a hard way to identify palindromes. Okay, there are more than that, but I want to talk about a string-based method and I want to talk about an integer-based method. We're always going to start with integers, but there's an easy way and a hard way to do it. When we're storing these numbers, what should we store them as?
Integers?
Ints or integers? The primitive int or the wrapper class integer? We talked a little bit about the difference between an int and an integer. The integer has a capital I because it is a class, a wrapper class that wraps around this primitive int and has an int as its field, as well as some additional methods that support what we can do to ints, or what we would like to be able to do to ints that the primitive doesn't support. We talked about one of those methods. Does anyone remember what a useful method of the integer class might be here? So this needs to be some actual instantiated value here, not actually an integer. So somewhere up here you have like an integer I equals something. It could even be null to start with. But you can now, it could be, you know, it needs to eventually be one of these numbers. But once it's one of these numbers, you can call the .toString method and it will return a string that you can store. Once it is a string, what does the string class have that would be able to identify a palindrome? That would be breaking it apart, yeah, but there's actually an entire function built into the string class that would be super useful here. Reverse, yeah. So we would want to check for something like is.
What's the method called?
It would just be reverse. So here we can check for the equality. Is this a shallow copy or deep copy check with dot equals? It's a deep copy check, yes. We're not checking if these are the same object. Once you call s dot reverse, you're gonna get back a different object than the original object. So you want to check their contents. If the contents of those string, if the arrays of characters that are inside of those strings are the same value, then you want to return true, otherwise you want to return false. So this is the easy method utilizing the integers toString method and the strings reverse method. But I also want to introduce, before we run out of time, the harder method, because it's just worth knowing algorithmically. I would never argue that this is what you should implement in person, because it's not necessary, but it's also just intriguing to see that you can also do this without strings at all, by just manipulating math, just manipulating these numbers. Does anyone have any inkling what that might be? What would be a process to check whether or not some number, a primitive int, is a palindrome without using any method support, just writing your own logic?
Subtract.
So yeah, we kind of want to be able to look at the positions, but there's no like char at method that we could call to figure out what's in a particular position.
Oh, models.
So yeah, we need to use modular arithmetic. So what we're going to do is we're going to take the original int that we're going to call I, and maybe, you know, we're going to check that it's a particular palindrome. 1, 2, 3, 4, 3, 2, 1. Something like that. And then we're going to start with an int reverse. We're going to set that equal to 0. We also need a copy of I, because at the end of this process, we're going to start manipulating I. So we need to store off a copy of it somewhere so that we can compare it at the end. So what process can we do to figure out what a some digit of I is? We don't necessarily, it's going to be difficult to figure out what the middle digit is. Is it easier to figure out what the first digit is or the last digit is of a number? I hear someone say last. That is right. Why?
Modulus of 10 and it'll give you the remainder.
Yeah, it doesn't matter how long the number is, mod 10 will always give you the value of the last digit. We don't know how long this number is, and there's no easy way to figure it out. I mean, you could keep like dividing it by 10, dividing it by 10, dividing it by 10, and then based on the result of that, how many times you iterated that before it terminated, you'd know where the value of the first digit is. That is so much unnecessary logic. It's so much easier to start with the last digit. So we need to write some kind of loop that's going to modify either I or copy, it doesn't matter which. I'm going to modify copy. That says something like, while copy is greater than or equal to 0, we want to first store off the mod 10 of it, and then we're gonna divide it by 10. And then we're gonna continue doing that process where we figure out what the last digit is, and then chop off that last digit. Figure out what the last digit is, chop off that last digit. Figure out what the last digit is, chop off that digit until it is 0. Once it is 0, we have gone through that process for every digit. While we do this, we want to build up what reverse is, because the last digit of I is going to be the first digit of reverse, right? So first, we need to figure out how to modify copy. So these two lines are gonna be what allows us to figure out what the mod is, and then remove that from the end of copy. So right now, somewhere stored in copy, 1, 2, 3, 4, 3, 2, 1, we're storing off this last digit, 1, somewhere, so mod 10 is 1 at the moment, and we're lopping this digit off of copy. We want to kind of push this 1 into reverse, such that the first digit of reverse is 1. So we need a couple things that are gonna help us to do this. So multiplying reverse by 10 is gonna shift everything in reverse over a place, making room for one more digit. This is what happens when you multiply something by 10, right? You kind of shift everything to the left and add a 0 at the end. And now if that, to that result, we add the value of mod 10, which was the value of that last digit, that's going to add that digit to the end of the numbers so far. So reverse right now is 1. 0 times 10 is still 0, plus 1 is 1. And now we just loop this process until copy is 0. I want to say greater than 0, not greater than 0. That will never terminate.
If we're looking for a 0 to end it, then we wouldn't be able to find the palindrome that's up there, with the 9009, because the 0 would then terminate it, causing it to break.
Copy would be 9009, and then it would be 900, and then it would be 90, and then it would be 9, and then it would be 0. So we're not looking at individual digits, we're looking at the left sum number of digits in the number.
Okay.
And only after we process the whole thing. That's a great point, and would be a big issue if that were true. But yeah, thinking critically, I love it. So continuing this process, looping back around, copy is still 1, 2, 3, 4, 3, 2. So that's bigger than 0. So we're continuing this process. Mod 10 is gonna be now this 2. So we're gonna have this be 2. We're gonna lop this digit off because we're dividing it by 10. Integer division says that whatever the remainder happens to be, we're moving this decimal place 1 over. Integer division says we lop off anything after the decimal. So it gets rid of this number. Then we're going to multiply reverse by 10, which kind of shifts this 1 over a place. And then we're going to add the value of mod 10. Looping around. Is copy 1, 2, 3, 4, 3 greater than 0? Yes. We come into the loop. We calculate mod 10, which is this value mod 10, which is 3, last digit. We then divide this number by 10, integer division, moving the decimal point over here and then lopping off everything after the decimal point, which gives us 1, 2, 3, 4. Then we're going to multiply reverse by 10 and add this 3. As we continue this process, eventually we'll eliminate the entirety of this number and we'll be replacing it in reverse into reverse. So the last thing we need to check here is whether or not I, the original number, because copy got modified, I is equal to reverse. If it is, it was a palindrome. If not, it wasn't. And that's actually what, basically, this concept of toString and reverse is doing for you just as characters. It's manipulating the positions of the characters rather than the position in an array, rather than the actual numerical values. So these end up being equivalent logic. And again, I don't want people to implement it this way necessarily, but I feel like it's an important mathematical outcome to see that you can modify primitives with logic like this that does something relatively complicated like check for palindromes. Are there any questions about any of this logic or code construction? All right, we only have a few minutes. I can stick around for a few minutes to answer any exam questions that people have, but again, if you'd like to submit a working example of largest palindrome product to me, if you can iron it out and get it working, send it to me. I'll give you a few points of extra credit somewhere. Any questions before we disperse? I will also be in my office after class if you have any individual questions about the exam. Reminder that the exam is tomorrow in person on paper, so don't try to zoom in tomorrow. It will be really difficult for me to hand you an exam. See you all in person tomorrow.
Thank you.